This lecture is about the complex natural logarithm of a complex number, z written in Cartesian coordinates as x plus iy, or in polar coordinates, which we'll find handy in the next video, r e to the I theta. As always, the argument theta is restricted to be minus pi less than theta less than or equal to pi. So we begin by recalling that the complex exponential is defined in our textbook as e to the z is e to the x plus iy is equal to e to the x times cosine y plus I sine y. So we do that splitting into real and imaginary part and use the real and imaginary part separately to make a definition. Other textbooks define it differently. They start with Taylor series and define the complex exponential e to the z as the infinite sum of z to the power k over k factorial. Both definitions give the same function, and later we're going to show that these things are equivalent. Either definition can be used to prove some important facts, which are always true about the complex exponential. So for instance, e to the 0 is 1, and e to the z1 times e to the z2, multiply two exponentials together, it's the same as adding the z1 and z2 first and then taking the exponential. And this is always true for any complex number z1 and z2. It's also true that you can never get 0 as an output from the exponential function. Nothing in the complex plane gives you 0 when you take e to the z. All of those said, we then later discovered a surprising fact that not only e to the 0 was equal to 1, but e to the 2 pi I, which was cosine 2 pi plus I sine 2 pi, which is 1 plus I times 0, is also 1. So there's more than one number that has the same value of the exponential function. So the exponential function is many to 1. Similarly, e to the 4 pi I is 1, e to the minus 2 pi I is 1, e to the 6 pi I is 1, e to the minus 4 pi I is 1, and so on. Every integer multiple of 2 pi I gives you 1. Every odd multiple of pi I gives us minus 1. And again, that's just a consequence of the definition. So now we want to move on from the complex exponential, which I assume you've actually seen. This is just recollection. We want to move on to the logarithm. So I say that by definition, if you have a number w such that e to the w gives you z, then by definition, w is a natural logarithm of z. And I use this article deliberately because we're going to see that there's more than one possible natural logarithm of z. We write w is ln sub k of z, where k is an as yet unspecified integer. This is an unambiguous notation because there is no other possible meaning for the subscript on a natural log. If I leave the subscript off, then I mean in particular that the imaginary part of w is trapped in this principal range, the same as the principal range of the r e to the I theta, so that we have minus pi less than the imaginary part of w is less than or equal to pi. This is called the principal branch of the logarithm. There are a lot of other notations for the natural logarithm and the principal branch. So here we're using ln z for the principal branch and ln k of z. This is not in any textbook. There's no textbook yet that uses that notation. This notation was invented by my colleague David Jeffrey, and I think it's an excellent notation and completely unambiguous and really useful. We'll see exactly what I mean later with this. But for now, it's just the distinction between the principal branch and any other branch. Other books use ln of z and capital Ln of z to mean the principal branch and any other branch. Sometimes they flip it around and they say that some other books yet use capital L to mean the principal branch and ln to mean the any other branch. Some books use log and capital log, so there's some ambiguity that way because of course log can also mean common log. Mathematicians tend to be a bit snobby and say those other uses are not important, and we never ever want to use the common logarithm. And that's true in this course, because what matters to us is differentiation. And when you differentiate common logs, you get an extra factor coming in. But mathematicians are not the only people in the universe, and so let's unambiguously use ln, a natural log, because I really am talking about natural log. I've had mathematical training, so I might slip and use log, but laugh at me if I do. These notations are not universal even in textbooks. Euler used just L. He just said L of Z to mean logarithm. And Stirling used L comma Z for the common log, which is kind of interesting. So now we have a definition that says e to a logarithm of Z gives you Z. And that's always true no matter which logarithm you use. E to the logarithm of Z is Z. Unfortunately, there are some things about the complex logarithm that we wish were true but are not always true. So we wish that the log of a times b was always the sum of the logarithms. That's true for real logarithms, and if a and b are both positive, this is certainly true. But it's not always true. And we wish that log of e to the z was always equal to z, and that's not true. It is true that e to the logarithm of z is always z, but it is not true that the logarithm of e to the z is always z, and I'll show you that directly. So if z equals 0, then e to the z is 1, that's true, and so the log of e to the z is the log of 1, which is 0, which is what we started with. Good. So it's sometimes true. But if z is 2 pi I, then e to the z is 1, and log of e to the z is the log of 1, which is 0, not 2 pi I, which was z. So it is not true that the log of e to the z is always equal to z. In the next video, we're going to explore that difference a little bit more carefully, and I'm going to define an unwinding number.